Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. It's been a while. We are back and we are talking about energy, which is unit 4. Is it unit 4? I think it is. Yes, unit 4, inshallah. And we'll be covering energy. We'll be talking about forms of energy. We'll be talking about how it's related to power. So let's dive into it. Okay, so today's lesson is Unit 4.1, and we are talking about energy, we're talking about work, we're talking about power. So we're going to be covering this topic over here, and then we are also going to be covering this topic over here. So this is basically the key question. What is energy? This is what we're going to be talking about. All right, let's get into it. So here we've got a paragraph, and as you used to, of course, we're going to go through the paragraph, we're going to be answering the questions. I would highly recommend that you bring your book along and you write the answers as we go along, and you check your answers with my answers. Did you know that wind can be used to produce electricity? I think most of us by now know that wind is used to produce electricity. A wind farm is a group of very large windmills or turbines placed in a location that gets a lot of wind. The energy from the wind causes the propellers the turbines, to spin. The turbines are connected to generators, and generators, of course, as the name suggests, generate or produce electricity. The amount of electricity produced depends on the size of the propellers, the number of turbines, and the strength of the wind. Very good. So here we are asked to write an answer. Analyze costs and benefits. What are some advantages and disadvantages of using wind energy to produce or create electricity? Right. So this is something that we have discussed in class. Now I want you to think about it. What's going to happen on a day when it's not very cloudy? Because obviously, when it's not very windy, those turbines, those wind generators, they use wind. So if it's not very windy, then it's not going to produce a lot of energy. So some of the advantages immediately, we can see some of the disadvantages and some of the advantages. Some of the advantages, someone might say that let's have a look. So we're going to write advantages over here. Advantages, which are good things. Advantages, it is environmentally friendly. And what that means is it doesn't produce toxic gases. Environmentally friendly. How is it friendly to the environment? It doesn't produce toxic gases. It doesn't produce carbon monoxide, methane, carbon monoxide, or any of that stuff as are we used to with fossil fuels. What other advantages are there? What other it is wind is infinite. It doesn't end. It is renewable. Okay? And what this word means, renewable, is that basically if we run out, there's always going to be more wind. So it's renewable. What are some of the disadvantages though? What are some of the disadvantages? Well, we've covered some of them briefly. Let's see if you remember. Disadvantages, think about it before I write it down. Disadvantages. Okay, and I might actually use red for disadvantages. The first one I can think of is it's not always going to be windy. It's not always windy. And of course, since it depends on the wind, it's going to be affected by the amount of wind we have. What else? What else can I say? I'm looking at my notes over here. It can take up a lot of space. It takes a lot of space. Because these are quite big. I'm not sure if you guys know, but back in Palmerston North, where I went to university, we had about 150 of those. And these are massive. So each one of those would take the footprint of a residential block here in Kuwait. Yeah, so it's quite big, right? It takes a lot of space. And let's not be mistaken, it does have an environmental impact. So even though it's environmentally friendly in one way, in a sense that it doesn't produce carbon dioxide, doesn't produce any bad gases, it is still not quite environmentally friendly in another way. And how is that? Well, if you're taking up space, then you're going to have to cut down some trees. You're going to have to dig underneath, and so you've also taken over the homes of some animals that belong to that environment. Okay, so it's not. So you can actually cause harm to birds and local life. Okay, and just like with anything else, obviously there are advantages and disadvantages. Okay, so let's get past all of this. How are energy, work, and power related? So here's the thing. When you see the word energy, I want you to think about work. Energy and work are very much related. Energy is the ability to do work. If you're out of energy, you can't do work. If you have energy, then you can do work. Okay, so that is the definition, the scientific definition of energy. It is the ability to do work. Did you put a book in your backpack this morning? If so, then you did work on your book. You did work on your book. Recall that work is done when a force moves an object. The ability to do work or cause change is called energy. Okay? Work and energy. When you do work on an object, some of your energy is transferred to that object. You can think of work as a transfer of energy. When energy is transferred, the object upon which the work is done gains energy. Energy is measured in joules, the same unit as work. That's very interesting. So now we know what the unit for work is, and we also know what the unit for energy is. Both of them are measured in joules, and the symbol for joules is J, capital J. So it's joules, that's the unit. Remember, the unit for length is meters, the unit for weight is newtons, the unit for mass is kilograms, the unit for work is joules, the unit for energy is joules, the unit for force is newtons. The symbol for joules is capital J. All right. So it's very interesting, though. There was something that was said here, and I'm just going to highlight it. And what was said was over here. You can think of work as transfer of energy, so that's all right. But then it says when energy is transferred, this next sentence over here, when energy is transferred, the object upon which the work is done gains energy. Now, that's very interesting. So basically, if I kick a ball, then am I giving the ball energy? Yes, yes you are. And basically what's going to happen is we're going to explore that further. So basically, let's say for example you're eating food. If you are eating food, you are transferring the energy from one form to another. Transferring energy. Okay. Let's watch the video and then we'll get back into it.
Energy is all around us. Scientists define energy as the ability to do work or cause change. We cannot see energy, but we can see the things that energy does. Energy makes things move. It powers the machines we use. It can make things get hotter or produce sound. Energy is used to light up our homes and cities and power the vehicles we use. All organisms need energy to grow, reproduce, and carry out life processes. Plants use the light energy from the sun to make food in the form of sugar. This energy is passed to animals when they feed on plants and other animals. There are two main forms of energy: kinetic energy and potential energy. Kinetic energy is the energy of movement. Mechanical energy, sound, light, heat, and electrical energy are all examples of kinetic energy. You can learn more about these forms of kinetic energy in our related videos. Potential energy is the energy something has due to its position, composition, or state. The stored energy can be converted into various types of kinetic energy. Fuels, such as petroleum, gas, and wood, contain a form of potential energy called chemical energy. When these fuels are burned, the chemical energy is converted into light and heat. Potential energy due to an object's position above the ground is called gravitational potential energy. A rock on top of a hill has gravitational potential energy. As it rolls down the hill, the potential energy is converted into kinetic as it is pulled down by the Earth's gravity. An arrow in a bow has potential energy due to its position behind the drawn string. This is called elastic potential energy. The elastic potential energy increases the more the string is drawn back. When the string is released, the potential energy is converted into kinetic energy as the arrow flies forward. That's pretty cool. Be sure to check out our related videos to learn more about different energy.
Very good. Okay, let me just... Oh, I don't know how to stop it now. Okay. So basically, that video covered quite a bit. That's fantastic. So basically what we've learned so far is that energy is the ability to do work or cause change. Energy is divided into two categories. So we've got kinetic energy, which is energy for movement, and we've got potential energy. And turns out that energy, which we normally think of as its own category, for example, sound and heat and and things like elastic energy and nuclear energy and chemical energy, and what else do we have? And vibrational energy. Turns out they all fall into those two categories. And we're going to explore this further. Now, before I carry on, I also want to mention a point over here, is that energy can't be created or destroyed. And I've mentioned this before, but I just want to remind you of it. Basically, what that means is that you cannot create energy. You can't make energy. You can only transfer it from one form to another. So in order for you to get energy, you must get it from another source, and you transfer it. So if you want energy, you have to eat a sandwich. Eating that sandwich gives you chemical energy, which you then transfer into kinetic energy if you are moving, thermal energy for respiration, keep your body warm at 36 or 37 degrees Celsius, sound energy if you're trying to speak, so all sorts of energy. And of course, once you've used that energy, there's no such thing as used it. You've basically just transferred it to another form. And that is really interesting. So what that tells me is that energy is recycled, basically. So energy can be moved from one form to another. It can be moved from chemical energy to thermal energy to movement energy or kinetic energy, and it can be recycled, just like money. So I want you to think of energy as currency. You can't print your own money at home. Well, if you try, you'll get in trouble. So basically, you can take the money and you can use it and spend it and change it for services and goods. And you can basically sell those goods and get money, but you can't really make your own money, and you really don't want to destroy it. You can't destroy it. So it's like currency in a way. It's the currency of movement, of doing work. If you want to do work, you need energy, okay? And energy is what's needed to do work. Let's move on. Power and energy. Here we have another concept. We're talking about power. Oops, let's go back. Power is energy transferred over time taken. Now, if we're talking about power, if we say someone is powerful, generally speaking, the first thing that comes to mind is muscles, right? So if somebody's got power, they've got muscles. But in terms of science, when we're talking about power, we're talking about the energy transferred over the time taken. Okay, so what that means is, if you are able to do a lot of work, because remember, energy and work are related. If you're able to do a lot of work in such a short time, then you are quite powerful. Okay, you have a lot of power. If you do a lot of work in a short time, then you've got a lot of power. But if you do a little bit of work in such a long time, you don't have as much power. So let's explore this. You may recall that power is the rate at which work is done. Since the transfer of energy is work, then power is the rate at which energy is transferred, or the amount of energy transferred in a unit of time. Different machines have different amounts of power. For example, you could use either a hand shovel or a snowblower. So here we've got an example of somebody using a hand shovel, and here we've got an example of somebody using a snowblower to clear their driveway of some snow. Which one's going to do it? Which one's going to do it faster? Well, obviously, I think it's quite obvious that this person here using a snowblower is going to do it a lot faster. In terms of energy, which machine uses more energy? Well, turns out both of those scenarios use the same amount of energy. How come? Well, they do the same amount of work. Remember, the amount of snow is exactly the same. They've got the same amount of snow, so they're both going to do the same amount of work. What's different is they're going to do it in different times. It's basically like saying, if you've got a test and you've got to study for it, and let's say you've got 20 pages to read through. If someone does the reading in 1 hour and someone else does the reading in 3 hours, the person who does the reading in 1 hour has more concentration, but they've done the same amount of work. This is what we're talking about here. It's the same amount of work, but it's just more power, right? So let's answer this question here then. You could use an elevator or stairs to lift a box to the 10th floor. Which has greater power? So let's explore this. So you could use an elevator to go all the way to the 10th floor over here, or you could use stairs to go all the way to the 10th floor. Now, I think the answer is going to be obvious. The amount of power experienced here in the elevator is most likely going to be greater than the amount of power that's used in the stairs scenario. How come? Well, it's the same amount of work. Remember, you've got to go to the 10th floor. Here's the 10th floor. It's quite high up. And this is also the 10th floor. So in terms of work done, in terms of energy, it's the same amount of energy. Same amount of energy, same amount of work. Same amount of energy, same amount of work, same amount of effort. Right, so what's different then? What's different is the amount of time. The elevator is most likely going to take much less than a person going up the stairs. Right, so the elevator might take, for example, 1 minute to get to the 10th floor, whereas a person climbing the stairs might take 10 minutes, right? In which case, the elevator is going to have 10 times the power, right? So that is what we're talking about here. Basically, it has got to do with time. Don't forget, it is energy, it is work, energy, work, over time taken. Okay, so what about now the unit for power? So we've got energy. What is the unit for energy? The unit for energy is, come on, remember from the previous slide, the unit for energy is joules. What about the unit for time? The unit for time is seconds. So power has the unit of joules per second. But, it's a bit of a joke, power has another unit as well, and you might have heard this if you go to Excite Electronics, or if you go to Eureka, or if you go to one of those shops that sell electronics, you'll see that electronic devices have watts written on them. What is the unit for energy? What is the unit for energy? Is that a question or is that a statement? What is the unit for energy? And that's why you've got like hair dryers that say, for example, 700 watts or 1800 watts. Those are all units of power. What is the unit for power? Sorry, not energy. What is the unit for power? So energy is joules, time is seconds, and power is watts. Okay, so which one's going to use greater power? We already said the elevator, as it does it in a shorter time. Okay, let's assess our understanding. Okay, I get it. So now I know that since transfer of energy is work, then power is work done divided by time taken. That is what power is. Right, let's move on. What are the two types of energies? Right, so we've already talked about this, and hopefully most of you remember. There are two different distinct types of energy. Every single bit of energy that we've ever thought about falls under those two. There's kinetic energy, which is movement energy, energy falls under either kinetic or potential. Kinetic or potential. Potential means stored, kinetic means movement. And turns out there are some factors that affect the amount of energy an object has. So if we're talking about kinetic energy, which is movement energy, which is the energy associated with an object that's moving, I want you to think about the following scenario. Let's say, for example, you've got a ball that's going towards you, and if that ball is traveling at a certain speed, let's say it's traveling slowly, somebody's just sort of throwing the ball at you very slowly, you can catch it and it feels fine. Now, if somebody kicks that ball really, really hard at you, it's the same ball, it's the same ball, it hasn't changed, but suddenly it feels a lot harder. Okay, it feels more difficult to catch it. It might even hurt. Why is that? Well, the ball is traveling at much faster speeds, and if it's traveling much faster, that means it has more energy. So the first thing I need to talk about is that kinetic energy has to do with speed. If an object's traveling faster, it has more movement energy. And the same example I can use for a bullet, for example. A bullet travels really, really fast, and that's why bullets have such high energy. The other thing we can talk about is, let's say, for example, you're dropping rocks from a cliff, right? And you're just dropping them, you're letting go of them. You're not actually throwing them, you're just letting go of the rocks or the stones. If you're throwing a little tiny pebble, a little tiny stone, if you're just letting that go, then that's going to make a splash in the lake under the cliff. But if you're going to throw a big rock, a big boulder, for example, it's going to move at the same rate. It's going to travel at the same speed. But suddenly the boulder is going to make a much bigger splash. Right, why is that? Why is it that the boulder is going to make a much bigger splash? Because the boulder has more mass. So suddenly we know the two factors that affect the amount of kinetic energy an object has. If the object that is moving has more mass, then it's going to have more energy. The other way to think about this, let's say for example a cat and an elephant are both charging at you. So you've got a cat and you've got an elephant, and it's time to draw, I think. I haven't drawn in a while, so I'm going to try and see if I can draw what resembles a cat, hopefully. So here's a cat. It's not the best looking cat in the world. It's alright. It'll do. Here's a cat, and here is an elephant. Okay. It might not look like an elephant, but it is an elephant. So here's an elephant with the tusks and all, and the legs. Okay, and it's got a tail. So which one would you rather be charging at you? Let's say, for example, they're both moving at a speed of 5 meters per second, which is possible. 5 meters per second is somebody who is, it's like a human running, really. So let's say they're both moving at you at 5 meters per second. Which one would you rather collide with? And I think most of us would say the cat. Thank you very much. And the reason why we'd say that is because the cat would have less energy. And since the cat would have less energy, the impact is not going to be as massive. Right, so kinetic energy has to do with speed and it has to do with mass. Okay, speed and mass. So let's explore this further now. I want you to forget about potential energy for a bit. We're going to explore that in the next slide. But for now, let's just talk about kinetic energy. Let's interpret the diagrams over here. List the vehicles in order of increasing kinetic energy. Now, interesting.
Okay, and see, this is working. And we're...
Can you hear me? Hello? Yep. Okay, good. So as we were talking about before, we're going to be doing this question over here, this one here. The kinetic energy of an object depends on its speed and mass, as we've already discussed. So it depends on the speed and the mass. Okay. Use the diagram to answer the questions. Interpret the diagrams. List the vehicles in order of increasing kinetic energy. Now, in order to figure out which vehicle, whether it's the red car, the bike, or the blue car, has the most energy, we need to look at two things. Which one has the most mass? So in terms of mass, they seem to be, the cars seem to be quite similar, don't they? So this looks like it's more or less the same size as this. So we can generally assume that it's going to be similar mass. This has the lowest amount of mass. Well, this is the smallest one, isn't it? So since this one has the most mass and it's traveling the fastest speed, we can safely say that it's the red car first. Oh, increasing, in order of increasing. So they want the least first. So the bike first. Oops, let's go back. Bike first. Motorbike, followed by blue car. Because even though the blue car has a lot of mass, it is traveling slower than the red car. And then the red car has the most mass and is traveling the fastest. Number 2. Explain. Describe another example of two objects that have different kinetic energies. Explain why the kinetic energies are different. Okay, well, it could be anything. Let's say, for example, a bullet and a pebble. A bullet has way more kinetic energy than a pebble because it's traveling a lot faster. A rocket has much more kinetic energy than a paper plane, right? Because it's traveling faster and it weighs more. And there are many, many other examples that I'll let you think about. Let's move on. Now, kinetic energy, turns out kinetic energy has a formula. So we've already covered that kinetic energy has to do with mass and velocity, or mass and speed. But now we're going to talk about another concept. So they don't have the same amount of influence on the amount of energy. So what that means is this. So kinetic energy, as we said, kinetic energy means movement. Kinetic energy means movement. Right? And it's determined by two factors, and that is the mass of the object and how fast it's going, or the speed of the object. But it's not simply mass times speed. No, that's not what it is. It is, in fact, half times m multiplied by velocity squared. This is the formula for kinetic energy. So it's half times the mass times the speed squared. And what that means is, if we look at mass and speed, which one's going to have a bigger impact on kinetic energy? Well, it's going to be speed. The reason for that is because of this little guy over here, the squared. Whatever the speed is, it's going to have a squared effect, which means it's going to be 4 times or multiple times more influential than the mass. So I'll give you an example. Let's say, for example, I have a watermelon that I'm throwing at someone. Okay, so here's a watermelon and I'm throwing it, and I'm throwing it that way. And this watermelon weighs 1 kilogram, while another watermelon weighs 2 kilograms. So this watermelon over here weighs 2 kilograms. Now, if they're both traveling at 2 meters per second, that means the amount of kinetic energy in this one is going to be half times mass times 2 squared, half times 1, because the mass is 1 kilogram, times 2 squared, which is going to equal half times 4, which is going to equal 2 joules. Don't forget the unit for energy is joules. Now, what's it going to be here? If we have the same exact scenario, the only thing we're changing is the mass. It's going to be double the mass this time, so times 2. Once again, the speed is 2, so it's 2 squared. Half of 2 is 1. 1 times 4 is going to be 4 joules. So as you can see, it seems to be that doubling the mass doubles the energy. Doubles the mass, doubles the energy. Now, let's do this scenario again, but this time, we're not concerned with doubling the mass. We're going to keep the mass the same. Let's keep the mass the same, okay? So we're going to change that one to 1 kilogram. Instead, we're going to change the velocity, or we're going to change the speed from 2 to 4. So we've doubled the speed, but we've kept the mass the same. All right? So double the speed, keep the mass the same. Let's see what happens to the energy. Okay. So over here, the mass is going to be 1, same as the one above. Over here, the speed is going to be 2 squared. Over here, the speed is going to be 4 squared. Suddenly, you can see the impact of speed. Speed has a much more profound impact. How is that? Half times 1 is half, times 4 is 2. So this remains at 2 joules. But since we've doubled the speed, we actually have 8 joules worth of energy. So rather than doubling the energy, once you double the speed, you actually quadruple the energy. You make it 4 times. Okay? So speed has a much bigger impact on kinetic energy than mass. So even though mass does have an impact, obviously, bigger objects traveling at a certain speed will have a lot of energy, but it's the speed that actually has a bigger impact on the amount of energy an object has. Okay? And over here we've got some calculations. Let's have a look. So I'm going to take all of this off. Okay, I hope you don't mind. Unfortunately, I know some of you will be going, no. Well, the good thing about videos is you can pause them. You can use the following equation to solve for kinetic energy of an object. So we've already covered that. The kinetic energy is going to be half times the mass times the speed squared. For example, suppose a boy is pulling a 10-kilogram wagon. So here's a boy, and the boy is moving quite hard, trying to pull a 10-kilogram wagon. Okay, so this wagon is 10 kg. Okay, what are they asking of us? They're asking us to calculate the energy. How fast is the boy moving? It says here that he is moving at a speed of 1 meter per second. So the speed is 1 meters per second. The mass is 10 kilograms. Can we calculate the kinetic energy? Certainly. The kinetic energy is going to be energy, kinetic, is equal to, this is what this means. Energy, big E, small k, means kinetic, is equal to half times m times v squared. So it's going to be half times the mass, which is 10, multiplied by 1 squared. So it's going to be 5 joules. Or 5, capital J. Right, and that's what we have over here. Okay. Okay, so over here we've got a question to consider, and it says, what has a greater effect on the object's kinetic energy? Well, we've already answered that one. It's going to be the speed. Explain. Doubling the mass. I'm just going to explain it now. Doubling the mass doubles the amount of energy, but doubling the speed quadruples the amount of energy, as we have seen in this example that I've done over here. If you're not sure, please go back and watch the example once again. Okay? And that is in fact what's being said over here. So doubling the mass of the wagon will double the kinetic energy, however, doubling the speed will quadruple the amount of energy, which is why it's so dangerous when people are traveling in a car and they speed up. Okay, if you speed up, you actually quadruple the amount of energy. If you double the speed that you're supposed to be traveling, let's say for example you're traveling at 50 kilometers per hour, and you decide that you go and speed up and travel 100 kilometers per hour. Now, some people might think, oh, that's going to double the energy. It's not going to double the energy. It's going to quadruple the energy and most likely result in death, as the energy is now a lot more than it would be normally. Okay, let's do this example here. A girl and her dog are running. The dog has a mass of 20 kilograms and the girl has a mass of 60 kilograms. So this boy here has a mass of 20 kg, while the girl has a mass of 60 kilograms. Okay, and what are we looking at over here? Suppose both the dog and the girl run at a speed of 2 meters per second. So both running at the same speed. Calculate both of their kinetic energy. We already know that the kinetic energy is going to be using this formula over here. Okay, so it's going to be half times the mass times the speed squared. So it's going to be half multiplied by the mass of the dog, which is 20, multiplied by the speed squared, which is 2 squared. And that is going to equal, oh, we're not there yet. That is going to equal 40 joules. The girl is a very similar scenario, except now the mass is different. So the mass is 60 multiplied by 2 squared, and that is going to be 120 joules. Okay. Suppose the dog speeds up and is now running at a speed of 4 meters per second. Calculate the dog's kinetic energy? Well, you know what? We know that doubling the speed quadruples the kinetic energy, so I don't even need to work it out to know that it's going to be 160. But let's do it anyway. So it's going to be half multiplied by 20 multiplied by 4 squared. Well, 4 squared is 16, multiplied by 10, that's going to be 160 joules. Draw conclusions. Are your answers to questions 1 and 2 reasonable? Explain. Yes, they are reasonable. We expect the speed to quadruple. Sorry, we expect the speed to result in quadrupling the amount of energy. So that's exactly what happened. Yes, as of course, doubling the mass doubles the energy, doubling the speed quadruples the energy. That's the explanation. I'm sorry, I'm not going to write it because I don't have enough space. But basically, explain doubling the mass will double the energy, whilst doubling the speed will quadruple the amount of energy. Let's look at something else. So remember we talked about the different types of energies. We said that all energy falls into either kinetic or potential, and it's time to explore this potential stored energy. Okay, let's have a look. So you might have heard this when you're talking to a friend or you're talking to a teacher, and if they say the following, you know, this person has potential, or so and so has potential, or this device has potential. And usually what that means is there's some stored power or some stored energy or some way of like, oh, there's something stored in it that hasn't been released yet. And usually it's used in a positive way, like if a person has potential, they have potential of success within them that hasn't been released yet. So potential just means stored, okay? And we're going to explore that in terms of gravitational potential energy, in terms of elastic potential energy. Turns out you can store energy, and let's explore that. An object does not have to be moving in order to have energy. Some objects have energy as a result of their shapes or positions. Their shapes or positions. And we're going to talk about that in a minute. When you lift a book up on your desk from the floor or compress a spring by winding a toy, you transfer energy to it. The energy you transfer is stored, or held in readiness, ready to be released. It might be used later if the book falls or the spring is unwound. Energy that results from the position or the shape of an object is called potential energy. This type of energy has the potential to do work. Okay, let's just explore this thing on the side here. What is the unit for force? It's Newton, and the symbol is N. What is the unit for height? It's meters, and the symbol is M. What is the unit for work? Well, remember, work and energy have the same unit, which is joules. Oh, my screen is just so small. And the symbol for that is capital J. Mass is going to be kilograms. And the symbol is kg. And energy is going to be joules once again. And the symbol is going to be capital J. Okay, let's explore gravitational potential energy, which is potential energy due to gravity. Potential energy related to an object's height is called gravitational potential energy. The gravitational potential energy of an object is equal to the work done to lift it to that height. Okay? So it's got to do with the height of the object. It's got to do with the height of the object. Remember that work is equal to the force multiplied by the distance. Okay? Work is equal to force multiplied by distance. Interesting. Did you guys know that? If you didn't know that, that is another formula. That is a very interesting formula, because that actually, you can rearrange that and you can do it in a different way. Let's see, for example, energy is equal to weight, which is a type of force, multiplied by height. So that is gravitational potential energy. So if we're talking about gravitational potential energy, you can see that weight is a force, and distance is the same as height, and work is related to energy. So it's all related. It's all related. But you don't have to know this relationship. Okay? So if you're not If you don't quite get it at the moment, don't panic too much, because as we do some questions, it'll make more sense. So gravitational potential energy is actually equivalent to the weight and the height. Another way of writing this is this, okay? So energy, gravitational potential equals mass multiplied by gravity multiplied by height. Now, hang on a minute. Here it says two things. How come you're writing three things? Well, remember, mass multiplied by gravity is equal to weight. Remember that from grade 6. If somebody says, for example, if somebody asks me, what is your mass? My mass is 85 kilograms. However, my weight is measured in newtons. My weight is 850 newtons. Why is that? Well, it's going to be my mass multiplied by gravitational pull, which here on Earth is 9.81. We usually use 10 because it's close enough. So it's going to be 85 times 10, or 850 newtons. That's my weight. So this is exactly what's happening over here. With the gravitational potential energy, we just say the gravitational potential energy is equal to the weight multiplied by the height. And the weight is equivalent, of course, to the mass multiplied by the gravity. Okay, so let's have a look at these questions over here. Gravitational potential energy. Identify, circle the rock climber with the greatest potential energy. Well, the one with the greatest potential energy is going to be the one with the most weight and the most height. The most weight and the most height. Okay, so which one has the most weight? We've got this one over here, which has a lot of weight, and this one over here, which has a lot of weight as well. Which one has more height, though? It's the one in red shirt. So it says circle the one with the most weight. It's going to be that one. And the most potential energy is going to be that one because it's the most weight and the most height. And it says here, somewhere here it says, the height to be used is the rock climber's lowest foot. So that's the height. The height is 4 meters. Okay, and if we calculate the energy, so this one here has 600 newtons. So remember, it's weight times height. The energy is weight multiplied by height. So the weight is 600 and the height is 4 meters. The height is 4 meters because it's the lowest foot. So 600 times 4 equals 2,400. What is the unit for energy? Joules. 600 times 4, weight times height, 600 times 4. Over here we've got a very similar scenario. We've got a height of 4, but the person climbing has a weight of 400 newtons. So once again, weight times height equals energy. So we've got 400 times 4, which equals 1,600. So over here, oops, let me just use a different font. Over here it's 1,600 joules. What about over here? Over here we've got 600, a weight of 600 multiplied by a height of 1 meter. So the gravitational potential energy here is only 600 joules. Whilst over here, the last one, we've got a weight of 400 and a height of 1 meter. So the amount of energy is 400 joules. Okay? And that's how you do that. I'm going to go to this. Just calculate this potential energy, the height is, okay, so we've just done that. For the person with the most energy, it's going to be 600 multiplied by 4 meters. 600 newtons multiplied by 4 meters, which is equal to 2,400 joules. Oops. And then we've got a challenge. Where would the rock climbers at the top have to be to have half as much potential energy? So these guys here on the top, they're at a height of 4 meters. And they have energies of 2,400 and 1,600. 2,400 and 1,600. Now, if I take those guys from 4 meters down to 2 meters, what do you think is going to happen? Let's see. Remember, gravitational potential energy is equivalent to weight times height. So the weight I can't do much about, but what about the height? So if I take this person that's 600 newtons and I take them from 600 times 4 is equivalent to 2,400 joules, and I bring them down to 2 meters. So instead of 4 meters, I bring them down to 2 meters. What's going to be the energy now? It's going to be half. So that's all I have to do. So back to the question, this question here, where would the rock climbers at the top have to be in order to have their energy? 2 meters. Simple as that. So when it comes to gravitational potential energy, you have the height, you have the energy. Okay, elastic potential energy. We also have another type of potential energy, that is elastic potential energy, and that is the kind of energy that is stored in rubber bands. Normally I have rubber bands over here, but I don't seem to have one at the moment. It's not just rubber bands though, it could be anything that can be deformed and reshaped. So let's say for example you've got a bow and you bend it slightly and then you release it, it releases that energy. If you've got a rubber band and you stretch it and then you release it, it releases that energy. I've seen this, it's a horrible example, I hope you don't do it. But if you take a rubber band and you try and hit someone with it, okay, and you stretch it out and then you release it, it's going to cause some pain, right? But then if you stretch it out some more and you release it, it's going to cause more pain. Why is that? Well, turns out it stores energy. When you stretch it out, you deform it, but you're storing energy in it. And then you release it, it goes back to its original shape and it releases that energy. Now, if you stretch it out more, then it's going to store more energy. That's basically what happens. So let's read through this. An object has different types of potential energy due to its shape. Elastic potential energy is the energy associated with objects that can be compressed or stretched. For example, when a girl in figure 4 presses down on the trampoline changes shape. The trampoline now has potential energy when the girl pushes off the trampoline. The stored energy sends the girl upwards, much like a spring. So if you push down on a spring, the same thing happens. You're storing the energy, and then if you release it, it goes out, just like Jack in a Box or something. Right, so let's have a look. So it says here, organize these in terms of something. The energy stored in stretch objects, such as we're doing this one here now, such as trampoline, is elastic potential energy. Rank the amount of elastic potential energy of the trampoline from the greatest to the least. Where would it have the greatest amount of elastic potential energy? The greatest amount of elastic potential energy would be found here. Okay, that would be the greatest amount of elastic potential energy. At this stage, you've stretched the trampoline downwards, and as soon as you release it, it's going to release the girl upwards. So that is the greatest amount of elastic potential energy. This is the second, and this here is the third. At this stage here, the energy is already released. The trampoline has gone back to its original shape, so it's no longer holding energy. And with that, we can actually do the questions at the bottom. So far what we've covered is that kinetic energy is a type of energy associated with movement. It's related to mass and it's related to the speed of the object. The speed has a bigger effect on the amount of kinetic energy an object has. Potential energy is stored energy, and that gravitational potential, there are two types that we've covered: gravitational potential energy and elastic potential energy. Okay, and both of these have to do with the position and the shape of the object. Okay, let's answer some questions. The energy an object has due to its motion is called motion. It's due to its motion, it's going to be kinetic energy. Stored energy that results from the position or the shape of an object is called potential energy. It's got to do with the position or the shape of an object. Position in terms of course, gravitational potential energy, the higher it is, the more energy it has. And with elastic potential energy, it's got to do with the shape of the object. So if it's stretched out more, it's got more elastic energy. Summarize, what are the two factors that affect an object's kinetic energy? We've already talked about this. It's going to be the mass and speed. And finally, applying concepts. What type of energy does a cup sitting on the table have and why? So is the cup moving? Here's a table and we've got a cup sitting on top of the table. Is the cup moving? No, it's not moving. So therefore it's got gravitational potential energy. It's got energy due to gravity. It's pulling down on it. If I pull the table from underneath the cup, it's going to fall. So it's got a lot of gravitational potential energy, but it doesn't have a lot of movement. Okay, okay, get it. So now there are two basic types of energy, and they are kinetic, oh, kinetic, and potential. Okay, there we go. Fantastic. And here we've got a quick summary test. Let's do it together. Write the letter of the correct answer on the line at the left. The kinetic energy of an object is equal to 1/2 its mass multiplied by its speed. Yep. Multiplied by what? Multiplied by its speed squared. Remember, for the first one, kinetic energy. Oh, let's write it properly. So energy kinetic is equal to 1/2 multiplied by mass multiplied by velocity squared. So it's speed squared. So that's going to be A for that one. And let's learn to listen to instructions. Write the letter. So we write the letter. The gravitational potential energy of an object is equal to the weight multiplied by its height. Energy is the ability to do work or cause change. So that's B as well. And finally, I would like you to try and think about this one before I do it. Energy and work are measured in joules. Right, fill in the blank to complete the following. Okay. When you do work on an object, some of your energy is what to the object? It is transferred. And an example of that is, for example, when I kick a football, some of my energy has gone into that football, which makes the football travel faster. How is the ball traveling faster? I've given it some of my energy, and therefore now it's traveling faster. Power is the rate at which energy is used, or what's another way of saying that? Yeah, I guess we can say that. Power is the rate at which energy is used. Next. Okay. Potential energy results from what or position of an object? Shape. A stretched rubber band has stored or elastic potential energy. Potential energy. A change in an object's speed has what effect on its kinetic energy than a change in mass? Has a bigger effect. Why is that? Remember we talked about kinetic energy over here, and we said that the speed is squared, therefore it will quadruple the amount of energy. A mountain climber at the peak has more energy. Why is that? Because over here you will have much more energy than if you are climbing over here, because the height difference. Remember, gravitational potential energy has to do with height. The person over here is higher up than the person over here, and therefore will have more gravitational potential energy. Okay, so let's summarize. Energy is the ability to do work. That's the first thing I want you to remember. Energy is divided into two categories, kinetic and potential. That is movement energy and stored energy. Work and energy are measured in joules. Work is measured in joules and energy is measured in joules, so work and energy are measured in joules. Power is equal to the work done in a certain time. Power is equal to the work done in a certain time. Yes, hopefully you're aware of that power is equal to the work done in a particular time. And we've got kinetic energy is determined by the mass and the speed of the object. Kinetic energy is determined by the mass and the speed of the object. Okay, and what else have we got? Gravitational potential energy is determined by the weight and the height, and remember weight is mass times gravity, so mgh. M times g is the weight, and then the height is h. And that's it. Thank you very much. I will see you on the next one, inshallah. Hope you enjoyed that one. Bye bye.